electromagnetic circuit theory, and we introduced some new terms like MMF, flux, reluctance, and we saw the analogy of how the magnetic circuit can be solved just like electrical circuits, and we also got the analogs. MMF is equivalent to is analogous to EMF, flux is analogous to current, reluctance is analogous to resistance, and so on. And we have done one or two problems, and there are many problems with more complicated magnetic circuits are there in the books. We should practice. There will be in the tutorial sheets. So we will do some other discussion today, and there will be some numericals also on this topic in the tutorial sheet 4. So these ferromagnetic materials, is basically are used for making the electromagnetic electromagnetic applications. And the ferromagnetic materials are characterized by high values of relative permeability, that is mu r is high for as a ferromagnetic material. And the ferromagnetic elements basically are iron, nickel, cobalt, gadolinium, some alloys of iron are all there, are used as ferromagnetic material for making, electrical equipments like transformers, induction motors, alternators, all these equipments need ferromagnetic material to make the iron core, that is the core part. So in the ferromagnetic material, what you basically have is a piece of iron. We have done the derivation, we have done the numericals, we having some cross section, and there is the mean path, mean radius of the core. And suppose there is the windings, okay, suppose there is the windings, and as soon as you pass some current to the windings, there is a flow of the flux is generated in the core, which we call the magnetic core. It can be purely iron, okay, or it can be an alloys of iron and so on are used as the ferromagnetic core material. So this thing we did, and we also saw about this leakage flux. And for the time being in this course, we will not consider much on the leakage flux aspect. We'll just assume that they are constant, or they are there is zero leakage flux or very negligible compared to the actual flux that passes through the core. Now we know that B is equal to mu naught mu r. B is equal to mu h. This is the formula. So B is the magnetic flux density, Weber per meter square. H is the magnetic field intensity, and that is related by B is equal to mu naught mu r. Now there is an interesting property that if we, this H is depends on what? H will depend upon what? Anybody can tell?
Number.
So the current and the distance.
The current. Okay, so this current is a thing that is going to generate the flux. So we can keep on increasing the current, we can keep on decreasing the current. So as you increase the current, it will increase the flux, it will increase the H. Okay, as you decrease the current, the opposite thing will happen. So, but what is actually seen in practice is, as the current is increased or as the H is increased, okay, the B increases up to a certain extent, okay, and then it gradually saturates. Okay, so the BH curve basically looks like this, that as H is increased from 0, okay, suddenly there is a rise, and then it gradually rises, and then after a certain region, the growth actually stops, and then it gradually saturates. Okay, so this region where it looks like what? It looks like our leg. Okay, it looks like our leg where this part looks like our knee. So this is basically called the knee. So this is what the BH characteristics is. BH characteristics is in actual practice. It all depends upon the nature of the magnetic material. That is the nature of the ferromagnetic material or the core element, and it's R, mu R. So this is the BH characteristic. So it increases sharply from 0, then again the increase takes place. But after a certain time, for a certain age, this rate of increase of B reduces, and it actually gradually saturates to some saturating value of the saturates to a certain B saturation. Okay, so this is because there is a limit to magnetization. You cannot keep on increasing the magnetism to an infinite extent. There will be a limit. There is a limit to for the magnetization to get saturated. So this is basically the BH curve characteristics. Typically, it looks like this type of shape, this S-shaped curve with a particular region known as the knee region. So you see, initially the slope of the BH curve is basically hello. Please mute yourself, all of you. Otherwise I will mute and there will be no interaction. So the slope at h equal to 0, that is the slope as origin, basically gives the initial value of the mu r. And so you see that at different values.
Sir, shouldn't it give mu naught mu r?
Which one?
It
is basically it is proportional to mu r. Okay, mu assuming mu naught is anyway constant. So the slope is all the slopes are basically
Sir, in a medium of relative permittivity mu r, sir, H is related to B by mu naught or B by mu naught mu r.
Whatever it comes from the formula B by mu naught mu r. It is just coming from that expression.
No, sir, we divide by mu naught or mu naught mu r. Mu naught mu r.
Mu naught mu r.
It will be mu naught mu r.
Okay, sir.
No, why is there a doubt? Yeah, until and unless mu r is 1, it is mu naught mu r, both are there. Yes. So this slope basically is proportional to mu r, and you see that at every point the slope keeps on changing. You can keep on computing the slope. Okay, so at each point, so gradually the slope increases. Okay, and then again the slope decreases. So this is the initial slope. Similarly, there is a region which is basically called the knee region. Okay, this is also called the T. Okay, so this is the knee region where at the point T, this slope is somewhat maximum. Okay, so the slope is somewhat maximum. Not just I will not use the word maximum, but from this point the slope reduces. Okay, so this region is basically called the knee region. Okay, so maximum is somewhere else. Anyway, the maximum is here, but this is the point from where it starts reducing. So yeah, what I have done is I have drawn a tangent from the origin to touching the knee. So you see, at every point you have the different values of mu r. So what you can do is you can also plot mu r with respect to h. So what will happen if you not plot mu r with respect to h? If you plot mu r with respect to h, so mu r is equal to b by mu naught h, and as h is increasing, the b is reducing. Okay, b is not reducing, I am using the b is saturating. So as h is increasing, the mu r ratio will be mu r equal to b by mu naught h will be basically keep on reducing because h is going quite high. So the mu r characteristics basically look something like this. It is gradually increasing. At certain point it is basically maximum, and then it keeps on reducing because here though the h is increasing but b has saturated. So this is basically the mu r h curve. So this is the mu r h curve. So this is basically a property that is displayed by ferromagnetic materials. It has a saturating BH curve. Okay, so it increases as the UH increase, but up to a certain extent, after a certain rise in B, it keeps on falling and then it saturates. So this is the characteristic of ferromagnetic material, and each ferromagnetic material which have different types of characteristics. So as a designer, if you are a machine designer, if you have to design a transformer or if you have to design a motor, all of them are being designed. Okay, so you have to basically consider the magnetization characteristics of the material. and each of the material has different magnetization characteristics, which has to be provided by the the supplier. Otherwise, you cannot design because you don't know what is the magnetization generated for a particular age. So different material will have different types of magnetization characteristics. Okay, up to this. Any doubt on this, on the magnetization curve BH?
Sir, one doubt I have.
One. Okay, you go first.
Yeah, so the tangent at the knee, we are claiming that it passes through the origin. How is that like true always?
Hmm?
Sir, how
Which one?
can we be sure that the tangent at the knee point, where the concavity changes, the tangent there passes through the origin? How can we be sure?
No, this is actually, it is all experimentally observed. I will show in after this slide the actual VH curves from the manufacturers who provide this ferromagnetic material. Okay, but it is just an imaginary tangent drawn there, as if from there it is bending. Does it answer your question?
Yes, I was just confused about the origin, like how will it pass through
No,
origin?
a line is drawn from the origin to the point, it just touches the knee region. Now, the knee region is also not sharply defined, it is gradually bending. Yeah, any other question?
Yes, sir. I want to ask a very basic question, sir. Because last day when we were doing problems on this magnetic
Uh,
circuits, that time we took the relative permittivity as a constant value. Like for cast iron, you took 900. Sir, what does that mean, sir? Like here, the relative permittivity changes with the value of B and
so very good. What is your name?
Anubhav.
Anubhav, okay, I will answer this question in the next slide. But actually, in those numericals, because it was a numerical, I gave a particular mu r and asked you to solve with respect to mu r. Okay, but here
Yes,
you
sir.
see, in actual practice, for a given value of age, the mu r value changes. Okay, so for a particular value of age, there is a particular b, and then from there you get the mu r. So when you do the actual design, you will actually have to consider the ferromagnetic characteristics. I will show some characteristics in the next slide. Okay, so in that case, suppose that the same problem is given, but I don't give you the value of mu r, but I give you the characteristic. Then you have to basically look into the characteristics, get the mu r and use it in the problem. You understand what I'm telling? I will show that
Yes, sir.
characteristics. I'll show that.
Excuse me, sir.
Yeah.
Sir, but for same material, mu r does not remain constant throughout, sir.
What do you see from these characteristics? Is it constant?
No,
as
sir.
as I change age, it is at a
changing.
it is at a different point on the characteristics. So obviously that point will have a different mu r.
Yes, sir.
So the comment is that it is not possible to describe analytically the characteristics of magnetic material. Okay, so it is not, these characteristics, this curve, it may not be possible to give a mathematical expression to this curve, that you give a particular value of h and you get the value of b. Okay, so it may not be, it may not be possible to even do some sort of to generate a mathematical expression for this curve. Okay, in your mathematics, you must be studying function approximation, interpolation, and all those things. So what you have to actually work on is the characteristics provided by the supplier, the manufacturer. So it is customary to get the relevant information about the magnetic characteristics of the sample from the manufacturer's, specification sheet based on the magnetic quantities of the test samples. The manufacturer, when you buy such an iron core, okay, the manufacturer will give you the VH characteristics of that core. Then only you can work on it. Otherwise, you cannot work on it.
Excuse me, sir.
Yeah.
Sir, the mu r h you have shown maximum at point T, but you also say that maximum is not at T.
No,
sir, maximum will be before point T, I think.
It will be before point T, wherever your gradient is maximum. Okay, I've
yes,
just
so where
drawn
the
some
curve is changing is
yes, the curve is changing the slope.
yes,
okay, so Okay, after I will show these characteristics after some discussion, then I will show the character. It is there in the next slide,
Sir,
not this slide
please.
also there.
Sir, please explain the knee point again.
Knee point is the point from where it, the name is given knee because it looks like a knee. Okay, the slope gradually increases from the origin. Okay, then at certain point the slope reduces and then keeps on reducing only and unless it saturates. So this bend is given the name of the knee because it looks like the shape of our knee.
The point from where the slope starts decreasing is
yeah, in whatever way you define knee. Yes.
Okay, sir.
Now there are some more interesting things in this. If we plot this H versus B characteristics, so what we just now show this, suppose from the origin we keep on increasing H. Now before going to this, I can also tell another. I should tell another thing is, suppose this you see in this ring there is a direction of I given. Okay, for this direction of I there will be H in one direction. The flux will be in one direction. If I change the direction of I, the flux will be in the other direction. Okay, you are sure about it? In the current diagram, the current is in one direction. So see here I have seen for this direction the H is positive. But if I reverse the direction of this current, the flux will be in the other direction. And in that case, with respect to the earlier H, this will be the H in the other direction. Okay. So this I can be changed. Okay, so now the current is going through the top terminal. It can be coming out also from the top terminal. Okay, so that is the thing that happens in AC. Okay, so right now I have shown a current going in one direction. It can be increased or decreased in that direction, but it is also possible to reverse the direction of the current. In that case, whatever H we are showing in the positive direction, it is possible to generate H also in the negative direction. Okay. Okay.
Sir, if we use AC instead of like DC current here, due to hysteresis, won't the B flux line start lagging behind the current?
Whatever the thing you are telling, I have those terms I have not yet introduced. I will gradually introduce, and then things will be clear. Okay. But right now you should appreciate that the current is going through the positive in the top terminal in this direction. It could be in the other direction also. So for this, if we consider H as positive, if the current is going out, we will consider H as the negative because the flux lines will also, direction of flux will also change. Okay.
Yes, sir.
So now if we keep on increasing the flux, as I told you, if we keep on increasing the flux in the positive direction, okay, so and up to a certain limit of H max. So starting from the origin, starting from 0 H, I keep on increasing the flux in a particular direction up to, in the positive direction up to H max. You see, this is the graph we have got. This is how it increases, and it reaches certain B max. Okay, it will reach a certain B max and it will saturate. So we have increased H up to H max in one direction, and it has reached A. Now suppose if we reduce it, okay, so suppose from this H max we start reducing H. Okay, suppose if we reduce H, what will happen?
B will start reducing.
B decrease.
Huh? B will decrease.
B will decrease, yes.
B will decrease, but if you want
not along the same path.
It will not follow the same path.
Yeah, experimentally it has been shown that it actually follows a different path. Okay.
Yes.
It follows a different path. So what happens is even at 0 H, there is some flux density also already present there at 0 H. That means it is not entirely demagnetized. There is a flux density, even there is no H, there is a certain B. So if we further reduce H, that means further reducing H means we have to go now towards the negative H. That means the direction of H has changed now. So it is 0. Now from reducing H means the direction of the current has to change. So if we further reduce H, Okay, that is in the negative side, negative. This will be negative with respect to the earlier. So what will happen is, for a certain value of H, negative H, then only the flux density will become 0. And if we still keep on increasing, if you keep still on changing the H, go further negative, okay, so then and go up to a certain H max, minus H max. Okay, so this was plus H max, we go up to minus H max. Then it follows again a certain the saturating characteristics in the opposite direction. So it is basically the same core. It is basically the same core where we are the magnetization is taking place, but in the other way. So it reaches some minus B max. Okay, it reaches some minus B max at certain D. And then again, suppose if we want to, if we change this, so we have change the direction of the current. Now, if we again change the direction of the current, what will happen is, it will again start to demagnetize, but again in the opposite way. And at a 0 H, basically again there will be some negative flux density in the other direction, but not exactly 0. So if we further again increase, so again we increase in the original direction, in the original positive direction. So all this we can do because we have the control on the current. So if we again increase this, what will happen is, again at a certain, certain H will be required to demagnetize it from the negative direction to make it as a 0 flux density. And then again, then from here again, if we increase, it will again go like this. Okay, so you see this, what we have done is, by this, is we have progressively, change the direction of H. First you increase the H up to a certain level, then again you decrease, and we found that at 0 H, even there was some retained magnetization. It needed some negative H to make it 0, and then again we went in the negative direction so that it saturates to certain flux density. Again it goes back and so on. So these original characteristics from that 0 state, that is 0 condition, never happens. So it keeps on changing like this. Okay, so this, see, we name all these points. Okay, we name all these points by some alphabets because they are the points through which these characteristics pass. So you see, there's this amount of flux is retained even if your H becomes 0. Okay, so that is a certain flux. So this OB is basically called the residual flux density. This is the residual flux. That means even if the H has become 0, there is a flux retained there. So this is called basically the residual flux density, the OB part, the value of OB, the magnitude of OB. Similarly, you see this OC. OC means what? That is basically the negative H that you have to provide to make it 0, to make the residual flux go 0. Okay, so this is basically known as the coercive force. Okay, so that coercive force have to be applied to make it 0. So this ferromagnetic material, which is used basically to make the all the electrical equipments, everything in your household fan, any other component you can think of, your that tube light choke, everything is basically ferromagnetic material, and they basically have this type of characteristics. So so as now H is changed, it will go here, and go here, and that this way it will keep on. It will follow this path, and this is going to happen because the supply is basically AC, so it will basically track this path to and fro. Okay, so this is basically known as the hysteresis loop. Hysteresis means that it retains some memory. You see that even if H is becoming 0, there is a residual flux present. Whether it is coming from the positive to the negative or it is going from the negative to the positive, the same type of some residual flux is retained. So the hysteresis word basically means something which is in memory. So this is basically the hysteresis loop, the hysteresis property that is exhibited by ferromagnetic materials. That makes the core of any electrical equipment. Okay.
Sir, I have a question.
Mm.
Sir, as soon as we go towards C, where the flux density within the core becomes 0, and suppose if we stop supplying the current, like if we stop giving any value of H from there itself, that is at point C, then also will it follow this path, or will it have 0 magnetic flux density
No, if it has reached C, then it is basically the at the point C the flux density is 0. Then what do you
Yes.
want to do?
Then I'm saying that instead of increasing the instead of increasing the H further in the opposite direction, what if we just stop the supply and make H 0 at C only? Then also will it follow this curve, or will it start from the point O again?
What do you think? If you have stopped the current, then there is no residual magnetism. Okay, so if you have stopped the current, so then if you start, where from should it start?
O only, I think.
It should start from the origin, because no residual magnetism is present.
Yes, sir.
Okay, so this was a question by whom?
Tanmay Datta.
Tanmay. But I thought that you could have done a more difficult question. That instead of stopping the current at that point, if from there only I start again making positive. Okay, as
Yes.
Tanmay told that at C it is a certain negative current, and okay, you switched off. So if you switched off, it is becoming 0. There is no flux, there is no residual magnetism present. But from there again, if you start to increase, yeah, so then you have to basically do the experiment and see what actually happens.
Okay, sir.
Sir, to stop the hysteresis loop. Sir, to stop the hysteresis loop completely.
Yes.
Sir, we have
Sir,
to apply this cycle of magnetism and demagnetism with an AC supply with decreasing magnitude amplitude. Sir, it would then reduce to 0.
Yeah, so you have to check it, what actually happens, because this is the magnetic characteristics is also not entirely understood. Okay, so
Sir,
I will.
But if for the same material, even if we make the correct direction positive in that case, when it is at C, then also, finally it would make the same loop for the same material.
No, but from C, in which direction will it go?
Sir, I think it will intersect OB.
It will somehow.
So will it have same shape, but it will come from C2 again to A?
Yes. That is what I am meaning.
Yes, that is.
But C to A, it may not happen, because this is the negative current. Okay, but then it will be shifted actually. It will be shifted. It has to be done experimentally. What is the characteristics? So this is basically the specification sheet. Whenever you buy some piece of core to make a product. Okay, so whether you buy cast steel or cast iron or transformer sheet steel, the companies will provide this type of BH characteristic. And as somebody asked, yesterday's problem, I gave a particular value of mu. Okay, and you did the problem. But if you are given this type of BH characteristics, from whatever is the value of H, you have to find out from the curve what is the value of B, and then go ahead with your numerical. Okay, so these type of sheets are actually provided by the sheet manufacturers. Okay, if you buy a transformer grade sheet steel from Tata Steel, okay, as soon as you buy, if you just bring the sheet steel at your home and think that you can work, you cannot work. You have to ask the manufacturer, you have to ask Tata Steel to give you the magnetization curves. Because using the magnetization, because that sheet steel produced by Tata Steel will have a particular magnetization curve depending upon the types of steel. Different types of steel are possible depending upon the different combination, composition. If it is an alloy of iron, it will also have a different VH curve. So these magnetization curves are very important.
Sir, please show the previous slide.
This slide is more important anyway. Okay.
Okay, sir.
So these are the magnetization curves provided by the sheet steel manufacturers. Okay, like if you buy sheet steel from Tata Steel, if there was a company in Howrah which is called Geskin Williams. They were once upon a time very famous manufacturers of sheet steel, which is used in if there is anybody or one of you from Howrah, you will know that there is a company called Geskin Williams. They were very famous for sheet steel, and all the sheet steel throughout India was provided by them for manufacturing transformers, motors, etc. Geskin Williams. And if you buy sheet steel, they have to give this type of specification, because you cannot without, and this specification is given by the company because they know the composition of the steel. They will actually do experiments on generate the data and give you this type of characteristics, the magnetization characteristics, which will be actually required for designing for troubleshooting. Okay. So the next thing is, so this is basically the magnetization curve. Now, so this is the thing we just studied. That is the hysteresis curve. Okay, all of you can see.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so if you keep on increasing H up to the positive, then go reduce it, become 0 and go to the negative. Again from negative you make it 0, go towards the positive. So basically it will keep on tracking this curve. It will just keep on tracking this curve. And that is the thing that is going to happen in, inside any core, because the current, if the input current is an AC, it will keep on changing in every cycle. For half of the cycle, it will go in one direction. For half of the cycle, it will keep on going in the other direction. So this cycle, so with one cycle, this hysteresis curve will also be crossing one cycle. So this one single curve is just for one cycle of the AC. So if for a certain increase of current from I to I plus DI, so if you have somewhere some current I flowing, and then you increase the current from I to I plus DI, so what will happen is, so the magnetization force, which H, it also undergoes an infinitesimal change by, say, PQ. So if there is at P there is the current I, and then that Q there is the current I plus DI. So the magnetization force changes by DH. Hello. Sir, I am taking a class up to 4. Can you call after 4? My class is going on. So at P, suppose the current was I, and at Q, so at P there is a certain H. And now if I increase the current to I plus DI, so there is a certain increase in DH. Okay, so that PQ is basically the DH. So you see that as current increases from I to I plus DI, your H increases by DH. And so if H increases, what happens? There is also a change in what? There is also a change in flux density inside the core. if there is a change in H by dH, there is a change in flux density inside the core. So flux density also increases by dB, which is basically given by this. If you increase the flux by dH, sorry, if you increase the magnetic field intensity by dH, the flux density basically increases by dB. Okay, so this is clear.
Yes,
It
sir.
is so at a particular I, suppose at P the current was I, and at Q the current becomes I plus DI. So basically your H has increased by DH. So that will basically result in change in flux density inside the. You have to mind that my language. I am talking flux density B. B unit is Weber per meter square or Tesla. The flux density increases by dB. So if the flux density increases, what will happen? It is Weber per meter square. So there will be correspondingly a change in flux. So to find the change in flux, what you have to do? Multiply the flux density by the core area. Okay, so there is a change in flux density by dB. So the flux change, which is d phi, is basically equal to A dB. If the cross-sectional area of the core is A. Okay, so the flux change density, the flux actually changes by A dB. And this is the thing which is of our interest, because we are only interested about the change in flux, which will actually result in some EMF generation. Okay, so you see that the instantaneous EMF that is introduced is basically given by N d phi dt. Any EMF induced is basically given by N d phi dt, and if you substitute that d phi, you basically get Na dB dt, the instantaneous EMF that is introduced. So what we have done is we have introduced a change in the current. Okay, so the change in current will introduce a change in H. The change in H will introduce a change in B. The change in B will introduce a change in phi. The change in phi will basically has the potential to increase the change in EMF by N d phi dt, which is Na dB dt. So so what actually happens is the instantaneous power supplied to the magnetic field. So since you are changing the current, you are basically providing power to the magnetic field. So the power supplied to the magnetic field basically becomes P is equal to EI. So if you just substitute this E and I, you get, because basically NIA dB dt, and the unit is in watts. The instantaneous power supplied to the magnetic field. So if we have changed the current by DI, so that will result in an instantaneous power supplied to the magnetic field is as NIA dB dt. And so the energy supplied is, since we have got the power, then the energy supplied to the magnetic field will be what? Which is equal to
PDT.
PDT. Okay, so this is basically NIA dB. So energy supplied to the magnetic field, and the unit is in joules. So all this is happening because we have actually changed a certain amount of current. So the energy supplied to, and all this goes into the core in the form of the energy to the magnetic field, which is given by NIA dB. So,
Sir, why did we ignore the negative sign in the equation for P?
No, negative sign is for for the directions, but what we are concerned about is the amount of power that we are giving. That is basically with the EMF generated. But the amount, when we are considered about the power, we are only concerned about the magnitude.
Means in all cases, power supplied is always positive.
Huh?
In all the cases, power supplied will be positive.
Power magnitude wise, it is positive. No, it is basically the EMF induced somewhere. But what we are considered is how much energy we are giving from outside.
Means what I mean to say is there any case in which energy is supplied from the magnetic field to the source?
That also can, that if it is the other way around, then we will have to change the convention. But right now we are providing energy from outside. If we have such a situation, we'll have to think of that. So now you see that P at P, the value of the magnetic field intensity was H. So OP was H. And so H is equal to Ni by L. We did yesterday. H is equal to Ni by L, MMF by the length of the magnetic circuit. Okay, so Ni by L. So here you see I is equal to OP L by N. I is equal to, just from this relation, I is equal to OP. OP means the field intensity into L, the length of the magnetic circuit, divided by N, the number of turns. Now if you substitute this I into this dW, the energy supplied to the magnetic field, you get, just we are doing some manipulation. If we substitute this I into this dW, so you get what? N is, as it is, I is OP into L by N into A into dB. And so this is equal to what? N and N will cancel. Okay, N is there in the numerator, denominator will cancel. So you are left with OP into L into A into dB. What is L into A? Can anybody tell what is
Volume.
Volume of the magnetic material. Okay. So since it is energy, the unit is joules. Everywhere you must be very much careful about the units. I am writing down the units. So it is joule. So, so L into A is basically the volume of the core. L into A. L is the mean length of the magnetic path multiplied by A. Whether it is the circular shaped ring or even square shaped ring. So that is basically the volume of the core into OP. So that means we are at a particular value of the current I, where the field intensity is OP, into the dB. Now OP, if you see this, if you come to this diagram, this is a infinitesimal change in current. You mind the word infinitesimal, that is a small change in current. Small change in current will result in a small change in dH and result in small change in flux density dB. So OP into dB means what? OP into dB?
Sir, area of that small scale.
Area of this hatched area.
Yes, sir.
Okay, this shaded area is basically OP into dB means the area of this shaded region. Okay. So the area of the shaded region is basically the equivalent to the energy supplied to the magnetic field. So in the BH curve, this small area is basically, if there is a small change in current, we just showed that small area is basically the energy supplied to the magnetic field, the area under that BH curve, that small area. Now if you do this over the whole, so it is basically V into the area of the shaded strip. V, that is the total volume of the core, into the area of the shaded strip. So, so if you find out per unit volume, okay, so if you just 1 minute, if the energy supplied is considered per unit volume, so it is just the area of the shaded strip. Yeah.
Sir, I was not able to hear. Can you please tell what is V?
What is V?
Yes, sir.
V is L into A.
Volume it is.
It is L is the mean length of the magnetic path. A is basically the cross-sectional area. So, length into that cross-sectional area is basically the volume. Okay.
Okay, sir.
So if you consider the energy supplied per unit volume, so it is basically the energy area of the shaded strip. Energy supplied per unit volume is equal to the area of the shaded strip. So the energy supplied to the magnetic field when H increases. So if you do this incrementally over small regions, so the energy supplied to the magnetic field as H increases from 0 to OC. Okay, so the energy supplied as an extension to the earlier derivation, energy supplied to the magnetic field when H increases from 0 to OC is basically the area what? This whole area is basically the whole area. Okay, at zero you are at the point T, because this will keep on continuing. So when it is from 0 to OC, so it is basically the whole area EF AGE. So as the H increases from 0 to OC, so it is basically this area EFAGE. Okay, so as the H increases from 0 to OC, it is basically that area EFAGE. But at C, what happens?
It should be J.
Sir, G or J.
Huh?
Sir, there should be AJE should be, sir.
AJE.
Yes, sir. EFAJE.
Yes, sir. It should be AJ, I think.
Huh?
G is outside the curve.
So what?
So it should be AGE.
You are increasing. So it is basically this entire area.
Yes, sir.
You have gone from here to here. Okay, even this AJ part is not at all there. Okay, when you are going from O to C,
Okay, sir.
it is going from E to A. So it is. So this is the energy supplied. But at C, what happens?
Yes, sir.
At C again you change the direction. So at C you change the direction. You change H. So energy returned to the source from the magnetic field as H is reduced from O to C. So at C what happens? It basically traces this path AJ. At C it basically traces the path AJ from OC to 0. It traces this path. So the energy returned is basically AGJA. So the energy returned to the source is basically AGJA. Because while returning it follows the path AJ. Okay. So the net energy absorbed by the magnetic material. So the energy given to the magnetic material was EF AGE. This was given and then it is returned while returning. That is AGJA. So what is the net energy given? Absorbed. Is basically the area under this BH curve. This part, whatever is the left, this area minus this area. Okay, so this area minus AGJA. So basically what you have is EFAJE, joule per meter cube. Everything we are doing per unit volume of the core. So the hysteresis loss in one complete cycle. So if you consider the hysteresis loss, in one complete cycle. So this is basically the energy that is going into that is taken by the magnetic field. Is basically the energy under this hysteresis curve. You have started the electromagnetic circuit, but this amount of energy is basically consumed by the magnetic circuit. DEFAJKD again back. So the entire area under the magnetic hysteresis curve is basically the energy loss in one complete cycle. It is taken by the magnetic field in one complete cycle. Sometimes the H is becoming positive, sometimes the H is becoming negative. It is passing through 0. So as it completes one cycle, this is the loss, that is the area under the BH curve is the amount of energy lost. Okay?
Yes, sir. I have a doubt.
Ah.
Sir, after completing one full cycle, if we repeat the entire procedure once again, then will the curve retrace itself or there will be some other type of graph?
Ideally, it will repeat itself. If the magnetization characteristics do not change over time, it will be repeating the same BH curve.
Okay, sir.
Isn't it the material property?
It is the material property, but if the material property changes with time, then something else can happen. But assuming that the material property remains the same.
Okay, sir.
So you see so what is happening in one cycle, the magnetic energy due to this hysteresis, this magnetic field is magnetic field is basically taking this amount of energy, which is basically called the hysteresis loss, because it is getting consumed by the magnetic field. We have just shown by this derivation that due to hysteresis, this amount of area, and which is exactly equal to the area under the hysteresis curve. Now the problem is to find out the area is very difficult because it is a very typical shape. Okay, and most of these are basically done experimentally. To get the exact area is impossible, to get the exact area under this hysteresis curve, because you may not have the correct equation for all these different parts. Okay, so this WH, that is the total energy that is absorbed by the magnetic field, that is the hysteresis loss, is basically area under the hysteresis loop. The area under, and so the area under the hysteresis loop is basically joules per meter cube per cycle. So in one cycle, this is the energy lost, the hysteresis loss. So if you find out the area of the hysteresis loop, it is basically the energy lost in one cycle per unit volume of the core. Obviously, meter cube is there. Okay.
Yes, sir.
So WH is
Yes,
equal
sir.
to the area of the hysteresis loop, which is the energy lost per meter cube, per unit volume and per cycle. In one cycle, this is the energy lost. So the area under the hysteresis curve. So WH is basically energy by volume into the cycles. So energy is what? P in power into time, which is volume per cycles. This is equal to power by volume into cycles per second. Power by volume into cycles per second. So here comes the frequency, cycles per second. So this is equal to pH by volume is V into F, the cycles per second. So you see that pH is equal to WHVF. pH, that is the hysteresis power, is equal to WH into V into F. So it is basically the hysteresis power loss in watts. Power unit is in watts. Hysteresis power loss in watts is proportional to WH, proportional to V, the volume, okay, assuming V to be constant, and F. So frequency of variation of H, that is in hertz, that is equal to the supply frequency. So based on experimental work, Steinmetz, there was an electrical engineer called Steinmetz, he developed an empirical relation to determine the power loss due to hysteresis. It is not possible to find out the exact area under the hysteresis curve. So Steinmetz developed an empirical relation to determine the power loss due to hysteresis. And he gave this formula that the power loss due to hysteresis is given by KHVF. It is dependent upon the maximum value of the flux density, B max to the power n watts. This is the formula given by Steinmetz. So where KH is a constant whose value depends on the material of the core and the range of flux density used. F is the frequency of the alternating magnetizing field in hertz. V is the volume of the core is fixed. And B max is the maximum value of the flux density in the Weber per meter square. So whenever you use a magnetic material, it will be suggested about the maximum value of the flux density that can be used. Because beyond that, N I'm telling, N is in some index. So N is basically called, it is named after Steinmetz. So it is called Steinmetz constant. N is basically given by Steinmetz, and the value of N basically lies from 1.5 to 2. Okay, so for a particular value of B max, for a particular value of n, okay, V is anyway constant, the volume of the core, KH is constant, you see that the hysteresis power loss is basically proportional to the frequency. You see the hysteresis power loss is directly proportional to the frequency. Okay, so the greater the supply frequency, your hysteresis power loss is going to increase. Now this
Sir,
value of
are
n,
we raising, sir, are we raising Bmax to some power n, or it is
yeah,
just an
Bmax to the power n, Bmax to the power n.
Okay, okay, sir. Okay, sir.
So this is the expression of the hysteresis power loss in watts. pH equal to kH Vf Bmax to the power n. Now V, the volume of the magnetic core is constant. kH is a constant depending upon the material of the core and the range of flux density used.
Sir?
And suppose if we can Bmax constant, wait just 1 minute, if we can make Bmax constant, then assuming some Steinmetz constant, then that is also constant. So you see the hysteresis power loss is directly proportional to the frequency. Yes.
Sir, if n is a variable, how is the equation dimensionally correct?
Yeah,
Yes,
n
sir,
is
the
not a
unit will change.
n is not a variable. N is a Steinmetz constant, and its value varies from 1.5 to 2, and depending upon the material, the value of n will be defined. Okay, suppose the value of some cast steel, the n is given as to be 1.6 or something, it will be given. It is not a variable, it is a constant that which is within this range.
Sir, but still, like if we have Bmax, unit is Tesla. So if the value of n is 1.5 in some case, then it will be Tesla to the power 1.5. And if it is 2, then it will become Tesla square. Then we will have two different units for two different kinds of material. Then the power unit may not be in watts. Then unit will change.
Constant
The unit of kh will differ, I think.
Yeah, in that kh will differ, but this is actually this is an empirical formula given by Steinmetz by doing thousands and thousands of experiments, because it is very difficult to calculate the area under the hysteresis curve. Okay, so he get an approximation formula which is kh Vf Bmax to the power n. This n will be defined by the material. Okay, and n is any value between this range. Hello. Just call me after 5 minutes, Okay. So we will stop here today. Then we'll go for the tutorial. So today what we have done is hysteresis loss. There is another more loss we will discuss in the next class.
Okay, thank you, sir.
Thank you.
Thank you,
Thank you, sir.